My computer is hot to the touch. I could fry an egg on it, probably. Okay. Well, I couldn't fry an egg because I'm vegan, but you know what I mean. Okay. Here's what I did. I did with lambdas. So, how does mine differ from yours? Let's pop open Python. Okay, I used 3 states, Q1, Q2, and Qn. What's going on here? I have some stack, and I have to initialize the stack here. All right. So, yeah, this is my initial stack with nothing on it. Which one of these is easier to read? I don't know. They're both pretty miserable. Okay. So I take a letter, and I take a stack. And so what do I do here? I do 3 operations. If s is 0, I append 0. And if it's not, I pop. And as soon as I pop off the stack, I change to Q2. In Q2, if S1 or S0, which is the beginning of the string, is equal to 1, I pop, and otherwise I return false. That's pretty much all. So the only thing this does is this makes sure that whenever I get to the last element of the string, I only have one thing left on the stack, and it's the character I'm missing. Not too complicated. Gazillion ways to do this. This is a very sort of internal state-oriented way of thinking about it. Each one of these states corresponds to one of your if statements, right? You're essentially measuring which if statement you're in with the states. I hope, and I didn't necessarily expect you to write this in any way, the way you wrote it shows a very strong correspondence between delta and if. Essentially what a delta does is I'm in a current state, and we can think of that as a line in the program, right? A line of code. And then the delta is you write an if statement, and the combination of the line of code and the test in the if statement is the same as the delta transition, and that transitions you to a different line of code. So I think in your line of thinking, when I say state, you should think line of code, because I think those are the same thing for you.
Yes.
Okay. Very good. Okay. Time for a formal definition. I know you love these formal definitions. Before we do this, no, I have to make you review. Okay. What are the 5 elements of a deterministic finite automata?
Initial state.
Okay.
Sorry, yeah.
You can do it in any order. Yep.
Sigma.
Okay.
Delta.
Yep.
And
You're missing 2 sets.
yes, one is like initial state, final state, accepting state.
Mm-hmm.
The one is missing, I guess.
It's just all the states.
String. Oh, sorry.
It was all of the states. So you said initial state. You said sigma.
Delta.
You said delta. And then the thing is the set of accepting states. And then the set of all states.
Okay.
Yeah. The other thing you said was string. The string is not part of the automata, right? The automata reads the string. And so that's sort of the difference between a function definition and a function argument or parameter or input. That's the way I would think of it. The other thing is to think, if you would like to think of the input as being part of the automata, sigma is the language of the input, which isn't quite the same thing as being the input, right? It's the set of characters that can be contained in a string, which is kind of goofy. Okay, so we have those 5 things. I'm going to do them in the order I'm used to, just to reiterate. All states, all letters, all transitions, start state, accept states. This is going to have one more thing. We have all of the states, Q. we have all of the letters, sigma. We have gamma. These are symbols just like sigma, but they are not the same as sigma. These are the chicken scratch for my statistics notes. This is the JSON file. This is the HTML encoding. This is not the finished product. This is internal storage. This is what I'm thinking about, but I don't tell anyone about, right? Sometimes, I think like even this weekend I've asked you like, hey, what are you doing? And you're like, oh, I need to think about it for a minute. That's the internal symbols, right? I don't see those. Yes. So inside of our mind, we have thoughts that we don't necessarily articulate, maybe because we can't, maybe because we don't want to, right? But whatever is up in there, that is gamma, right? And this little character here means gamma. You never have to say gamma in your life. If you don't want to, you can always say stack symbols.
Stack symbols.
Previously, we only had one type of symbol, which was the input symbols. Now we have two types of symbols. And you can also refer to these as the terminals and the variables in the context-free understanding. These ones are variables because they're internal. And we don't show them. We only show people the finished product that only contains the input symbols, right? So when a context-free grammar generates a language, it has variables and terminals. It generates a series of terminals. We take that string generated by the context-free grammar and we give it to a pushdown automata. The terminals of the pushdown automata correspond directly to the input variables of the pushdown automata, okay? All right, we've got the transition function, and that's a mapping. It's a non-trivial mapping, okay? I'm not going to pretend this one is simple to look at, but look at this thing. Okay. Let me talk through each one of these elements. Okay, well, let's just look at sigma first. Sigma is the input symbols, those are the terminals. We introduced that already. Baby epsilon here means that I'm allowed to also look at the empty string. So I don't have to read a symbol. What does this mean? Well, this adds an additional usefulness that I can either manipulate the stack or the input tape without moving both at the same time. Because sometimes I might read something and I don't care. Here's an example. We talked about the equal number of zeros and ones case, right? What if there's also twos on that string? We don't care. We can just read over the twos without thinking about them at all, right? I'm going to give you a decimal number that can contain 0 through 9, and I'm only going to ask you if it has the same numbers of zeros and ones. So whenever you see a 2, 3, 4, 5, 6, 7, 8, or 9 on the input tape, you just keep going. You don't care about that stuff. You don't manipulate the stack at all.
So you're going to keep more stacks?
Mm-hmm. Or, yeah, you can track it however you want, right? But if you're only checking to see if there's zeros and ones, you only manipulate the stack when you see a 0 or a 1. Separately, there might be times you only want to manipulate the stack and you don't want to read the input tape. This is in the case of a peek push operation. So I can always, I can't just peek, but I can say, I'm going to transition into a state where I pop something off the stack. And depending on what pops off the stack, I'm going to do a different operation. So in a sense, you can sort of hold the value of one of your stack symbols in your internal state in this way. Then you need more internal states to keep track of everything, right? But it's possible. So what we allow is we do not require you to read and write to both the stack and to, or I guess you read and write from the stack, you only read from the input tape. You don't have to read and write and everything all at the same time. You can do things in steps. Okay, so this is inputs. This is internals. And we are allowed to think about nothing at all. That's allowed. We can have our head completely empty and devoid of thought. That is legal. I don't know that I'd recommend it, but it's possible. Okay. And you take a state. I have the finite control is in some certain state. It looks at the tape and sees a symbol. It looks at the stack and sees a certain symbol. And what does it do? It decides what the next state is. And the next state is not just the state of the finite control. It also can write something to the stack, or not. It is allowed to write nothing to the stack and just leave the stack as is. And this thing is non-deterministic, which means that this is a set of possible future states and a set of possible stack write values. But it's a simple enough idea, which is that we just have something that's reading a tape and has some memory, It always guesses the right thing to write to the stack of every single possibility. And it just slowly moves down the tape, sometimes pausing for a minute to manipulate its internal stack. And that's all. That's all that's happening, right? Okay. Given a state, a letter, and a stack symbol, get a set of states and stack symbols. That's all. The states and stack symbols go with each other. This is an example of what it looks like. Given a state, a letter, and a stack symbol, I'm using C character for stack symbol and A alphabet for input symbol. Use whatever you want. Terminals, variables, terminals, variables, okay? And here's a possible state with a possible stack symbol, and here's a possible state with a possible stack symbol. Why did I select D and E here? These are alphabetically after C. I mean to denote that they are part of the same thing that C is part of, right? So I just use next. There's no particularly relevant way. Perhaps I could have expressed all of these as gamma sub 1, gamma sub 2, gamma sub 3, or something like that. I could have used lowercase gamma. I used C for character because I'm accustomed to that. Okay. In state Q, while reading A on the tape, and while reading C on the stack. Tape and the stack in two different places. There are two possibilities I can do in the future. Either I can update my state to R1 and write D to the stack, or I can update my state to R2 and write E to the stack. Those are the two possibilities. That's what this means. The initial state and the accepting state are identical to finite automata. No changes there. So all of the changes are to these two. We add variables, and delta gets way more complicated. And this is good that delta is getting more complicated, right? Because we essentially want a computer, and we want computers to be able to do things. And so, yeah, it's theoretically annoying to have to deal with a more complicated delta, but it's also like really annoying when you want to do multiple assignment in a programming language and you're writing C instead of Python and you have to use a local variable to do that, right? That is annoying. And it's like good annoying sometimes, in the sense sometimes we want to think about how much memory we're using, and it's bad annoying other times when we like just want to get the code to work quickly to see if something works, right? I really like that I can do this. That's just a nice thing to be able to do. And we would never allow a pushdown automata to do that, right? These are multiple reads and writes to different locations all at the same time in random access memory. That's crazy, right? This is modern computer stuff. What a pushdown automata has is it has some stack that contains nothing, and then we append a 1 to it, and then we append a 2 to it, and then we have to pop off the 2 at the same time. We do another pop, and then we append the value of that. And so, like, this is an extremely drawn-out operation. Yeah. But it's logically equivalent, right? Equivalent in power. Okay, here's an example. We're going to introduce the special reverse operation. You know what the reverse operation is. We'll reverse my name. Not too bad, right? Not the easiest thing in the world to write in an automata, by the way. But we can do that here. Okay. We're going to define this with Python. I used stressed and desserts, which is my favorite reversal. This is how I write. I called it superscript R because I didn't know what else to call it. Easy enough. Here. We'll just run this as is, and you can see it. Really wish it didn't prompt me that. Oh, I guess it's worried I'm going to like erase my hard drive or something, right? Reverse of stressed is desserts. Okay. So we're going to define a language. We're going to call it the language B. We're back into languages. And we're going to talk about automata in a second, but right now we're just defining this language, and then we're going to deal with an automata. It takes any word. What is a word? It's a sequence of characters. And it appends or concatenates the reversal of that word. So what we would actually have is we would have W plus superscript script RW. This would be an element of the language. And we're going to express this in binary. And there's some way to change everything in Python into bits. And I don't remember what it is, right? But can I see how long this is? Length. Nope. Okay, it doesn't have that attribute. Perhaps you've seen this before. Yeah, there's like bits all over the place in Python, and they're like partially obscured. Okay, so we're storing it as a bit string. Here's an example: 0, 0, 1, 1, 1, 1, 0, 0. This is the beginning reversed.
Oh.
Okay. Okay. So here's what I'm thinking. I'm going to read a symbol, like a 0 or a 1. This is why we use binary, because it's way easier to keep track of how many alphabet characters there are, right? When I read the symbol, I'm going to throw it on the stack. That's all. I'm going to have the same, after all that effort to differentiate variables and terminals, we're going to use the same thing for both, okay? Or perhaps when I see a 0, I push an A onto the stack, and when I see a 1, I push a B onto the stack. Same thing. So I'm going to read a symbol, and I'm going to push it to the stack. So I'm reading along my tape, I take the symbol, push it on the stack. Take the symbol, push it onto the stack, right? Okay. When I'm exactly halfway through my string, I stop taking things off of the tape and putting them on the stack. And I start looking at the tape, and then I look over at the stack and I make sure they have the same character. And then I take the thing off the stack and throw it out. I look, is it the same? Yes, take it off the stack and throw it out. I look, it's different. Oh, I reject the string. Okay. Easy enough. Here's one little problem with this. We have no idea how long our string is. So here is an example of a string that can be reversed. 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0. Oh, how do you know when you're halfway through? There's 4 repeats. You don't know. I have an ingenious idea to solve this problem. Our machine is non-deterministic, so it doesn't matter. We can just always say, look, we will assume any possible case is the middle. We will check every single one of them. We will, correspondingly have higher memory and computation costs. Doesn't affect me, I can still answer it eventually. We don't care about how good our performance is, we just care that this is possible. So we check every single point to see if it's halfway through the string. So when we look at the empty string, before we read a single character, we say, we could accept here if there's nothing after this. And then we read one character and we say, well, we can't accept here no matter what, because this is an odd length string. But after that, you push it on the stack and you read it. And so we have a non-deterministic stack value. Something important to keep in mind about this is that when we are executing non-deterministically, with the non-deterministic finite automatas, the only difference was there was differences in the internal state. Now we have internal state and we also have stack. Each non-deterministic branch, if you branch with an if statement, they get their own stack. This should make perfect sense to us, because if I write an if statement in Python, and then I define a variable inside that if statement, that only affects that if statement. That variable is not defined outside that if statement. The same thing with functions. So this matches our intuitive understanding of programming languages. Something we say often with starting programmers is they have no idea where variables are defined, and they don't understand variable scope, and they don't understand anything. What this means is it should be surprising that our programming languages do have an internal logic that makes sense, because it seems like people are bad at understanding that. Well, they are. But this automata theory that had essentially what is the notion of local stack. Chomsky put this together in 1950 before Fortran existed, which means the idea of having a dedicated stack frame for your function is older than stack frames and functions and computers and programming languages, right? All of these problems had been solved logically by linguists before the first programming languages even existed. And that's why our programming languages make any sense at all, right? Okay. What do we do if we see the stack is empty? Well, frequently, for example, with the see if I have the same number of zeros and ones, the thing is you read to the end of the string, you check if the stack is empty, and then you return true if it is. Well, how do you see if the stack is empty?
Check everything.
But there's no value in the stack. We can't see if the stack has some value. This is just one of the cases where we it doesn't actually matter that we said we could see the stack is empty, but it is very important to note when we wrote our delta, we wrote it over the stack alphabet, which means it can only read letters off of the stack. It can't read the absence of letters off the stack. We didn't include the empty string in there. We didn't include the empty language in there. There was no notion of any of these things. Don't worry. It was completely reasonable to assume we could do that, but I'm going to give you an example of this. As we get to more and more sophisticated automata, we're going to hand wave more and more details away. We're just going to have a novel symbol. Usually I denote it this one. I use octothorpe. And we're just going to say, every time my pushdown automata comes on, the very first thing it does is it writes an octothorpe, or a pound sign, or a hashtag, or whatever. Shift 3. Writes shift 3 onto the stack, and that is a variable. It is not part of the input alphabet. It is not. It's just a special symbol that only exists on the stack, and I'm only going to write it once. And instead of saying if the stack is empty, I'm going to say if this symbol is on the stack, because it's the same. Necessarily write it in the first state, and then we add new states to deal with that variable. So these simplifying assumptions are a useful convenience that doesn't adversely impact rigor or change results. If there's a way we can model it, we can just say we're going to model it that way from now on. This is the same notion we did with showing we can use non-determinism or determinism for finite automata. It's the same thing we did when we say my edge labels in my generalized non-deterministic finite automata can contain regular languages. We can make these simplifying assumptions, assume them, and then just use them later. And so we can always say there's a way for me to check to see if the stack is empty. I have demonstrated I have a way to do that. Now I'm just going to say I can always see if the stack is empty, and I won't have the extra. Okay. We're not going to do this exercise because we're a little bit behind on time. Do you need a break?
Yes, we can rest.
Yeah, take 5 minutes.
Where is the restroom?
Want to know any machine learning? Just click on a different link on my website and go to that page. I upload all of those as well. Display capture. Okay. What are we going to do now? The pushdown automata to me are, I mean, they exist almost purely as an academic exercise. So my understanding is Chomsky was at MIT in the 50s and 60s, and there was this known correspondence between regular languages and the DFAs. We will go on later, and Turing machines are actually equivalent to two different languages, recursive languages and recursively enumerable languages, and that's because Turing machines have two different amounts of power. There's things that they recognize and things they enumerate. Those are different, right? And so I think Chomsky was hanging out probably with the computer scientists, and they were like, why don't you have an automata that corresponds to CFGs? And so we just made one. And so they exist almost purely as an academic exercise, right? Finite state machines are used in like systems theory and systems thinking and programming language design and so on. But even in programming language design, you'd use a context-free grammar instead of a push-down automata. It's just a little bit too silly to have a stack and nothing else, right? The only real usefulness of it is to demonstrate, yes, no matter what language we come up with, there does exist some corresponding automata, pretty much. And it is important to note that there are languages in between the finite automata and the pushdown automata, because we're using non-deterministic pushdown automata, and deterministic pushdown automata are weaker. So there's this additional language class in there. It's just not an academically interesting language class, so we're going to skip over it. Versus finite automata, right? Essentially, I scheduled something like 7 hours on finite automata and 4 hours on pushdown automata. They're just a transitional state up to the Turing machine. What we're going to do now, and this took us, you remember, all day yesterday with regular languages and finite automata. We're just going to show the equivalence quite quickly here. Then we're going to show the pumping lemma for the context-free grammar. So we are going to do it on the grammar, not the automata. And then we're going into Turing machines after lunch. So before we do that, it is currently 11:08. Do you want to eat at the dining hall today? Because then we'll break for lunch 1 hour early, so it's still open. Or do you want to do the Indian food? What do you want to do for lunch? We can either eat here or go to the dining hall.
Dining hall?
You want to do dining hall today?
On the Starbucks?
No, there's like a whole like place that the undergraduates eat. It's like a cafeteria. Do you want to do that today? I just have to make sure that we're not still doing a lecture until 1 o'clock if we do that. Do you want to break for lunch in 1 hour or 2 hours?
1 hour is fine.
1 hour is fine. Okay. So we'll do the pumping lemma after lunch. Okay. All right. I showed you the schematic view. I showed you the language view. These two things are equivalent. I think it's non-obvious. When you see the proof, you'll say, why didn't I think of that? Because it's obvious as soon as you see how to do it. So let's go through that. So what are we going to do? If G is a context-free grammar, because it could be a grammar with context, as we've shown, and it could also be a poorly formed grammar that is not a context-free grammar or anything else. If G is a context-free grammar, then some pushdown automata recognizes A. What is A? A is the language produced by G. It is the language of G, or it is perhaps equivalent to G. And it is L of the PDA. It is L of M. So how are we going to say that? We're going to convert A's CFG to a PDA. No problem. Okay. For all G context-free grammars, there exists P, pushdown automata. The pushdown automata is a 6-tuple, which is the 5 tuples, or the 5 elements of a finite automata, and additionally the stack. The language of the pushdown automata is equivalent to the context-free language. So that's this context-free language. Okay. Let's start by looking at our alphabets. Okay, so how are we going to do this? Well, essentially, we can just use the context-free grammar as a way to program the pushdown automata. And this is where the terminals, variables, stack alphabet, input alphabet thing comes into play. P is our pushdown automata, and it is going to take the first variable. Remember, the variables are the things we do not return of the context-free language or the context-free grammar, or G, however you want to say it. So it takes the starting variable, throws it on its stack. Okay. We can almost think of this. I look over, I see the grammar, I take the grammar and I put the first variable on my stack. Okay, then what do I do? Let's think about this in terms of a specific grammar. This is the arithmetic grammar, plus and times, parens, things of this nature. So if we're starting with this one, our starting variable is the topmost and leftmost variable, not terminal. So we take E and we put E on our stack. Okay. So I have my pushdown automata has nothing except E on the stack. Okay. E is necessarily then part of gamma, the stack alphabet. This is the alphabet that is not part of the finite automata. This is how we model the stack. Okay. It is necessarily not part of sigma because it will not ever be on the input. I will never read E in an input string that I'm evaluating in a language. It's a special internal symbol. This is the same way if we represent zeros as A's on our stack or what have you, right? So we have to have the separate alphabet for the stack and the inputs for this reason. That's why it is a 6-tuple. Because you could argue, you could say, what if I just restrict my pushdown automata such that the only things I can write on the stack are the sigma values? Then it's not as powerful, because then it can't have its own internal thoughts, right? So we're not going to make any claims about whether the input variables are allowed on the stack, but we are going to say the stack variables are not allowed on the input tape. Okay. So this is sort of the same notion we've seen here previously. What have I done here? These are the exact same pushdown automata implementations we used previously. There is only one thing that changed here. Instead of pushing zeros onto the stack, I push on exclamation points. Exclamation points are not part of any of the input languages I'm going to check. There are no exclamation points in any of these. And it doesn't matter. This function works the same way. It's just going to read something off of the stack, and it's just going to write something to the stack. So I can use an exclamation point. I can use any symbol I want. So here's my strategy. I'm going to utilize non-determinism. And the way I'm going to utilize non-determinism is anytime I read anything off of the input tape, I don't know which context-free grammar rule it corresponds to, right? And let's recall what the rules are. The rule is a way of taking a variable and substituting it for some combination of terminals and variables. So anytime I see a terminal, I don't know from which, its predecessor, I don't know which variable was replaced to get that terminal. And I don't care. I just check all of them, non-deterministically. I loop over all of the possibilities, however you want to think of it, right? So we're going to utilize non-determinism. We're going to replace the start symbol S, and how are we going to replace it? We're going to write a substitution to our stack, okay? Non-deterministically, we write every substitution, and we will find out when one of them accepts, if it accepts or not, and then we will throw out all of the things. This is the trolley that goes down both sides of the tracks. This is creating a multi-process instead of having a branch every time. It's the same idea. Okay, so we're non-deterministically going to do every substitution over starting symbol S, okay? Let's follow this through. We're going to target A plus A times A with grammar 2. So we can maintain the stack. I'm going to go through here and I'm going to show you how I think of the stack maintaining. So we're going to start with E. We already discussed that. That's the starting symbol. It was the top of our grammar. Okay. So let's use Pythonic notation. We begin, we have an E in our stack. We always start with E in our stack. When our pushdown automata wakes up in state Q1, the first thing it does is it writes an E to the stack, and it does not read anything off of the input tape. It is only writing to the stack now. Okay? What's it going to do next? It is going to perform a substitution. Now, in fact, it performs every possible substitution. We are just showing one of the possibilities, and we are showing the possibility that is going to be correct. So I think E can also be substituted for T directly. Yeah, we also do that, but that's never going to get where we want to go, so we don't worry about that sort of branch, right? So we have E plus T, and we'll notice that the stack is looking an awful lot like our derivation tree. Okay, what's the next thing we're going to do? Well, this is a little bit different. T plus T. We can only perform one substitution at a time. So we're only going to make the substitution in this first position. Why is that? Well, we can only read and write to the first element of the stack. And we can only read and write one element at a time. So we're not going to mess with this whole side of the tree right now, right? Okay. So we replace T, we replace E with T. We're following this down. I suspect the next thing we're going to do is we're going to turn that T into an F. Does that sound like a good idea? Oh, we didn't do anything. That's okay. That's definitely supposed to be an F. That's okay. Yeah.
This one's supposed to be the right one's supposed to be F, right?
Mm-hmm.
T plus F.
Or F plus T, because it's this F. So we do E becomes E plus T. Then we do one more substitution. We substitute E for T. T plus T. T plus T. Then it's going to be F plus T, and then it's going to be A plus T. And the reason for that, do I have the grammar here somewhere? Ooh, the grammar is very far away. Okay.
Excuse me.
Okay. I sure hope that thing actually works.
Yeah, it's okay.
Very good. Okay. I'm going to go through which substitution we do in order. We begin with E. We begin with E. E, E, same E. Okay. We substitute E for E plus T. E plus T. Okay. The next thing I'm going to do is I'm going to substitute E for T, which is another legal substitution. Okay? T plus T.
T plus T.
And that corresponds to this here. We can only follow one arrow at a time, essentially. Now, the next thing I do is wrong, and I'm going to try and correct it. So, this is T plus T. That should be F.
F plus T.
Yes, because that is this F, and that is accomplished with this rule, which is that a T may become an F. Okay. This is a function that, given a T, returns non-deterministically either T cross F or F. We don't know its return value. So that should be an F. Okay, then what's the next thing we do? There's a little problem here. We've been manipulating this first column. This is not the top of the stack, which means that if I perform this right, I am writing to the bottom of the stack. That's not allowed. This is not a correct derivation. This is not possible. I'm going to make a note to myself to fix that. So what are we going to do instead? I'm going to close this window, and I'm going to make this large again. Okay. So what are we going to do instead? Well, we have only push and pop operations, but we can always push and pop. We can pop an E off the stack and then push a T onto the stack. That's fine. Do that right here. We pop E off and we push T on. That's fine. The plus and T stay on the stack. They're unaltered. Python tail pops. Oh yeah, this is the Python implementation, right? There's no graceful way to do this in Python because Python wants to be pushing and popping at the end, and I want to be pushing and popping at the beginning. So in all of my examples here, I just reverse things, push, pop, and then re-reverse it. That's not particularly graceful, but it does in fact work, right? Really, we should just write a custom stack. So we can pop a T off and then push a T cross F. That was one of our substitution rules. So T can become either T cross F or F, and you can review that. So this is, in theory, allowed, right? We take the T off, and we place T cross F, and there's still the plus T that persists on the stack. That's totally legal, right? We're writing to the top of the stack. We write first an F, then a times, then a T. Okay? We replaced the first T, so we can always replace the first thing on the stack. But this is not actually correct because we're trying to get to A plus A times A, and we have a times before a plus. So this isn't actually what we're trying to do. So, yeah, and that's just not our original target. If I go back here a gazillion, we're going for plus before times. We just stated that's our goal. One of the problems with stating goals is that oftentimes you can find some string, but unless you're finding the string you said you could find, you're not actually demonstrating anything, right? Okay. So, what are we going to do? We're only going to push and pop to the top of the stack. If we can access below the top of the stack, that is a different type of memory, that is a different type of data structure. We usually call that random access memory. What's an example of random access memory? No problem, I've got you. We create a list. Here's a random access. I can just look in the middle of my stack. That's not allowed. Pushdown Automata can't do that. We agreed they only had push and pop operations. Why did we agree they only had push and pop operations? That's how we get equivalence with CFGs. That's the only reason. The whole motivation of this is to show an equivalence, right? And if we have random access memory, what we actually have is this laptop. It is equivalently powerful to this laptop. Okay, so that's also equivalently power to the Turing machine, to Alonzo Church's lambda calculus, to Post's machine, which is equivalent to the Turing machine, and to Gödel's general recursion. Ah, yes, there we have. I think I learned in my undergrad they were just calling it Gödel's general recursion in those days. It looks like now people refer to it as generally recursive functions. So I have seen this term around a lot less, but it was an important part of my undergraduate training that there were these three equivalent formulations. And it seems like people have stepped away from that considerably, and now they're saying it's just the Turing machine and the lambda calculus that are equivalent. But in fact, Gödel demonstrated his earlier general recursion was equivalent to the Turing machine. His opinion was just that his general recursion was much worse to work with, so he switched to using Turing machines because they were easier to work with. So let's invent our workaround. Okay, we don't need to work with the bottom of the stack. Why don't we need to work with the bottom of the stack? Well, we're not trying to do this thing only on the stack. We have one other thing. We have an input tape. This T, which was this T that was causing us the problems, it's going to turn into an F, and it's going to turn into an A. And that A is going to live on the input tape. So what we just do is we keep doing substitutions at the top of the stack until we get to a terminal. Then we compare the terminal to our input string, and if it's the same, we pop it off the stack and never think of it again, and we move to the next letter on our input tape. So we have an A in both places. I move to the next symbol on the tape. I take the thing off the stack, and then what is the thing we see right after it? We're going to reorder our substitutions. How's this work? We start with an E on the stack, and we have read nothing off the tape. Now, the tape has something on it. We just haven't read it yet. This is representing our read history, not what's actually on the tape. What's on the tape is A plus A times A. And we're validating that that can be generated. Okay. We're going to perform a substitution, E plus T, T plus T. Here I have it correct. That is F plus T. A plus T. Ah, that's a terminal. So in the next step, after I get a terminal on the top of my stack, what's the next thing I do? I don't do any substitution operations. I do a deletion. I take A off the stack, and I read A off of the tape at the same time. I progress both. I throw out this A, and I read this A, and we can think of that actually as throwing out both A's. I just go on to the next thing. And what's the next thing? By golly, it's a plus. So I throw out the A, I throw out the plus, and then I have a T. Now this T, according to our substitution rules, can eventually be turned into A times A. And we know after seeing A plus A, the next thing we're going to see is A times A. So this way we're going to process prefixes. We always compute all the way up to our terminals. We pop the terminals off our stack at the same time we read them on the input tape, and we just show that they're equal. We just proceed. People often use this term lockstep because it's like the tape and the stack are marching together. A plus, same time. And then we do some computation. A times A. Nothing on the stack, nothing on the tape, we accept. So our new strategy is going to be to aggressively resolve to terminal symbols. We're going to get to terminals as fast as we can. We're going to copy the terminals to the tape. We're going to make sure they're in both places. Okay. We're only going to work on the top of the stack. We're never going to look deeper in the stack. We're only ever going to look at one symbol at a time. We're only going to perform substitutions on that terminal. And as soon as we can't substitute it, we're going to look over at the tape and see if the same thing is there. Here's the proof. Take sigma to be the terminals. Take gamma to be the terminals and the variables. Take delta to be write CFL's S to the stack. That's easy. So delta is just the context-free language. We're going to write the stack terminals to the tape. And there you have it. Apply rules. Okay, adjacent results. We convert a PDA back to a CFL, but it's non-trivial. When we converted a deterministic finite automata to a regular language, what did we do? Well, the first thing we did is we proved NFAs are equivalent to DFAs. Then we proved generalized NFAs are equivalent to DFAs. And in between those two proofs, we had to prove 3 closure properties and the atomicity lemma. That's about how involved this is, right? This is 5 theorems worth of work. My assessment is that I am probably going to look at this proof and see how it feels to me, and then maybe this will be your assignment for the second week. And so this lecture is called CFG to PDA, and then you will do PDA to CFG. You will write it in a Quarto book. You will publish it. You will share it on your LinkedIn. You'll say, hire me, look how good I am at writing code. And everyone will be suitably impressed. It'll be very exciting. For now, it is sufficient to know that this is the case. We're never going to use this result. It doesn't affect us. We have demonstrated how to go in one direction. That's sufficient. Every regular language is a context-free language. How do we know that? Well, regular languages can be modeled with DFAs. And a PDA is a DFA that also has a stack. So we simply say, PDA, do not use your stack. And then it reads a regular language. We've demonstrated that the DFAs can read context-free languages. So therefore, they can read regular languages are a strict subset of context-free languages. They're the ones for which you don't have to use the stack. So we just convert to automata and ignore stacks. Getting back to an idea I've sort of teased for a while. Automata accept and grammars generate. So a finite automata recognizes the languages created by regular expressions, and a pushdown automata recognizes the languages created by a context-free grammar. And then I should have one other thing here, which is just the name. Oh yes, there it's on the other side of the screen. I didn't even look at it. A regular language is recognized by a finite automata and generated by a regular expression. A context-free language, or a CFL, is recognized by a pushdown automata and generated by a context-free grammar. Okay. What does this mean? This means that any one of the 3 equivalent classes, language, regular language, FA, regular expression, these are a subset of the pushdown automata, context-free grammar, context-free languages. Every finite automata can be modeled by a pushdown automata. Not every pushdown automata can be modeled by a finite automata, but some can. Right? Yes. So the pushdown automata that recognizes the string that only contains zeros. Yeah. I can use the stack. I don't need to. But there is a pushdown automata that recognizes that language. It just so happens there's also a finite automata that recognizes that language. And there's a generalized finite automata that recognizes that language, and there's both deterministic and non-deterministic finite automata that recognize that language, right? I can recognize it with anything. It's a very simple language, but that means my more powerful tools can still recognize it. And they can also generate it. I can also write the context-free grammar that generates the language that only contains zeros. And how would I even do it, right? I'd have some start symbol S, and S would either be substituted for 0S or the empty string. And that's it. And that will generate an infinite number of zeros, the same way 0 star will generate a potentially infinite number of zeros. Okay. I like viewing these as Venn diagrams. There's other ways to view them as well, of course. This was the most natural way to me. I don't really love what this Venn diagram looks like, but oh, and I believe, I don't know if this is true, I was going to sit down and write this proof and I got sidetracked. I believe there is very close to infinitely many PDAs for every finite automata. I think there are infinitely more of these. So I think there's probably a bijection between like how many PDAs you can represent per NFA and the natural numbers. I don't know that that's true. I'm not going to give you that as an assignment because I'm not even sure how I'd go about that, but I bet there's that many. And one of the reasons to think there's that many is, well, you can have any countable number of stack symbols, and you can have any countable number on the stack, and if you put that together, that's starting to look a lot like the size of the natural numbers. Maybe there's some reason you can't do that because it doesn't actually matter how many letters you have, right? But it gets there. So how many more? Many more. There are, of course, things that are bigger than PDA, and that is Turing machine. So this is just part of our Venn diagram so far. I wanted to do a code reveal on this. I used the matplotlib pyplot, which you're familiar with. You might not have been aware of matplotlib then, which I didn't know about. I found out about it for this class, so I thought I'd show you. This thing is basically, I'm going to say there's something of size 4, which is PDA, and I just picked a size. It didn't matter. I don't know if that corresponds to the radius. I don't know if that corresponds to the area, right? But this is just a tuple. This is a keyword argument that is equal to tuple. So I have an overlap of 1, and then I have a non-overlap of 4. The thing with non-overlap is PDA, and the thing with overlap is star FA. Then I'm going to turn off a bunch of labels because the labels looked very confusing. I'm going to plot this. I'm going to show the plot, and there it is. So if you ever want to make a model, oh, look, it's cute. It's showing the coordinates in the bottom. So I never want to show you a graphic that I don't also show you how to make it. And so I found out about this matplotlib Venn diagram library and thought I'd show it to you. Okay. We usually get some questions about the context-free grammars, so let's go over some of those quickly. Why do we restrict ourselves to a stack? And I've tried to be clear on this. Only because we care about the context-free grammars. That's all. The stack just so happens to be the most common data structure that corresponds to how much more power a finite automata needs to do context-free grammar. It is unsurprising that this is a stack because we should think in our minds, substituting those terminals is an awful lot like stack push-pop operations. So I think when Chomsky was spent 10 years thinking about this, right, he probably just one day was realized, oh, the context-free grammar is just maintaining a stack. It's identical. There are now existing constructed languages made by linguists, like for the sake of having fun, that are stack-based languages. So you can actually speak a stack-based language, right? And I suspect that if we trained people to talk this way, they would have a lot more fun. I don't know how every other language works, but for example, in Spanish, adjectives are suffixes instead of prefixes. So instead of saying red car, I say automobile rojo, and rojo is the second word, a modifier. That feels a lot more like a stack operation when you realize, oh, modifiers can go on either side of the noun. What's actually happening is, in English, I pop red off the stack, and I remember it's going to modify the next thing. In Spanish, I pop the noun off the stack, and then I wait to see if there's a modifier in the next position. Perhaps it would make sense if we were all making an effort to communicate clearly with each other as humans if we just like agreed on a stack order of operations. We can show this in another sense too, which is that Python has something I actually don't love, but many people do love, which is that plus is an infix operator. We have infix linguistic operators as well, and the most obvious one is that and is both an infix logical operator and an infix linguistic operator, right, as a conjunction. I don't love this very much, but we have ways of doing this with and, which we just say all, and that is the same logical operator. So we can convert sort of some of these notions we do in programming languages to being stack-based operations. And I think you can do this from operator import plus. I don't recall, but there are prefix addition operators in Python, and we can just write one real quick. This is an equivalently logical way to express arithmetic to me. There's not a great way to do postfix, which is the way English nouns modify English adjectives, or you could equivalently say the Spanish reversal, right? So we could say paint equals lambda s red plus s, and I can paint my car. So we can do prefix that way as well. And then we can do, ooh, do I know Spanish? I think Spanish for paint is pintar. And so I think we can pintar and auto, and we can get auto rojo. So there's ways to think of these stack-based operations as being things that exist in languages as well. What's your first language? You're not a native English speaker, are you?
My first language is Hindi.
Hindi? I don't know any Hindi. Do you put, how would you say red car?
Red car is lal car. Lal gadi.
Okay.
Lal means red.
Okay, so it is
means,
prefix,
yeah.
same as English. Okay.
Same as English.
Okay. So it's a prefix language. Okay. Okay, here's another one in English where the modifier comes second. I run fast. So that's a postfix modifier on run. How do you say I run fast in Hindi? Yeah.
This one is prefix.
That one's prefix. Okay,
Yeah.
so there's even another difference between the languages, right?
मैं तेज भागता हूँ.
Mm-hmm.
I fast run.
I fast run.
Literal translate to English, it will
Yeah.
like.
And perhaps that's closer to English, like I quickly run or I rapidly run or something like that, right? We can sort of move these things around.
Yes.
Yeah, I think that's as far as I can get into language without my brain melting. But anyways, the linguists came up with all of this. We should give them their flowers. They did a good job. To me, the reason the Pushdown automata existed is my impression of other people, not necessarily of myself, and I seem to be in a minority in this for some reason. I don't know why that is. Seems like almost everyone would rather write proofs about automata than they would about languages. I have never felt that way in my life. To me, it's like, why are we keeping track of like all of these states and these arrows and these labels? It's like, just give me the language. I'll just write the program, right? I will write out an expression that shows the logical equivalence, and I'll put an equal sign in the middle of it. And you've kind of seen me do this because you've seen the heinous Python code I write where it's just this big list comprehension. It's like, well, that's just a language, right? I'm perfectly happy with the languages. Not everyone likes that. But yeah, for whatever reason, and Gödel was very clear about this. He came up with the general recursive functions. He was using them for, I think, 7 or 8 years before Turing came along. Turing reinvented them without ever having even heard of Gödel's thing, and Gödel says, Turing's is better, right? I don't agree, Girdle. I liked yours better, right? Like, you should have kept using that, right? But even both Alonzo Church and Kurt Girdle, who came up with their own equivalent expressions to the most powerful automatas, chose not to use the forms they came up with themselves because they found them so difficult to work with, right? And I think that they should have spent some years doing code golf in Python, and then they'd be fine. But here we are. Okay. Yeah, they're so lazy. They didn't learn to code, you know, because the pesky computers didn't exist for another 30 years. Right? It's interesting even to think about questions like, would anyone have ever made a computer if they didn't come up with the Turing machine? Because no one is ever going to implement a context-free grammar in electrical engineering, right?
Maybe.
Well, you can imagine you say to an electrical engineer, it's like, over here I have a stack and over here I have a tape, and they're like, I can build one of those. Like, I got it. Or perhaps all of the electrical engineers are much smarter than me, and they actually think they were just making lambda calculators, and they happened to make Turing machines by accident. Right? It is possible to prove properties of finite automatas and pushdown automata that we cannot prove of Turing machines. This is very interesting for a variety of reasons, which is that one of the things you would say is you're like, there's this thing a Turing machine can't do. And someone could come back at you and say, like, well, automatas just can't do that. And you could say, no. We can prove this property about a finite automata, and we cannot prove it about a Turing machine. And in fact, we can prove we can't prove it about the Turing machine, right? This is interesting. This means that there's some more sophistication and some more confusion in a Turing machine, right? They are fundamentally distinct, even though they are just mathematical objects. All of these things are just tuples, right? Tuples. All these things are just tuples, right? But like the way we use them can be markedly different. And one of the things that I can point out that we have seen is ambiguity. Context-free grammars can be ambiguous. Regular expressions cannot, right? Or not in the same way, right? And so it is an incomplete exploration of computing if you do not demonstrate there are some counterexamples to some of the things you would naturally assume, right? So we have to look out for that, and we have to be very careful with that. So even if a pushdown automata, to me it's just this most useless form of the automata that you would never use for anything. It's worse than the context-free grammar, right? But it's worthy of examination to understand what the other automatas look like and how they differ and all these things, right? So that is the compelling case for the pushdown automata. I don't expect you to go out and buy a pushdown automata and to replace your laptop and then write a bunch of programs on a pushdown automata, right? Like, that's not what I'm talking about. And then separately, if you're just thinking of this in terms of like, can I get better at thinking, right? Which is usually not how we think of things. Usually you go out and learn how to use containers, or you go out and learn how to use AWS, right? But AWS changes their interface every 2 weeks, and the pushdown automata has been unaltered since it was dreamed up the first time, right? So if you can learn to think about pushdown automata as well, like maybe that's a more generalizable skill that persists. So separately, there are many, many programs that you do not need the full power of a Turing machine to express. And one of the things I like to impress upon my undergraduates in particular is they seem to think they can use an infinite amount of memory all the time for any reason. And a lot of times I ask them something like, what is 6 times 7? And you do not need to use a fundamentally infinite amount of memory to solve 6 times 7, right? And so one of the reasons to show these restricted machines is to show how powerful they are and show that many times you don't actually need the full power of a Turing machine. The time this comes up most often I have seen is identity and access control for things like AWS, where you say, we have different users in our group that are associated with this API key, and some of them have this permissions, and some of them have that permissions, and some of them have the other permissions. And if these permissions in, administration gets complicated enough, you would start expressing it as an automata. And I think there's a temptation to reach for Python or one of these extremely powerful Turing equivalent languages to express. But frequently all you need is a finite state machine. If this, then that, done. You don't need a for loop. You don't need recursion. You don't need a recursive call stack, right? You don't need to do any of those things. You can express very, very many, very complex relationships with a finite state machine. And one of the examples I always give is any arbitrarily complicated traffic light can be expressed with a finite state machine. You never need a computer in there. Now, of course, you use a computer now, modern, because it's cheaper to buy a computer than it is to buy a finite state machine, right? But if I find out there's a memory leak in your code that wrote a traffic light, that was very, very bad, because you shouldn't have been using any memory at all. You should just have a loop. And it shouldn't write to anything, it shouldn't read to anything, it should just have a timer and it should update. So that's one way to think about all of this. One of the things I really noticed, my first job was putting humans in space. And we cared a lot about making sure we didn't run out of memory, because if we run out of memory and the computer is too slow, then the humans don't come back from space, and that's very bad, right? So people coming out of undergraduate, especially in the United States, I don't know what your experience was, they weren't very good at thinking about how much memory they used. And I was like, hey, if this concept of like when you put out the ailerons on your lander or whatever, right, if that can be expressed in a finite state machine, you really need to express it in a finite state machine and not use any of the memory, because we don't know how much memory we can use, and it costs a lot of money to make sure we're not using too much memory. And if we have to send additional memory into space, then we have to buy more chips and more processors, and it slows down, and there's more error handling and all of this stuff. And it's like, it's very important to not use resources you don't need in some contexts. This probably matters in cars. I don't think it matters in games. All of the games are unoptimized, right? And that's one of the main common softwares. My impression, having run Firefox and Chrome and Edge this weekend, is those don't seem as optimized as they could be, even though they're relatively high performance, right? And I think all of that's okay. But in embedded system space, if you're working for aerospace, right, Delta's here, Kia's right over there, if you end up working for one of those places, they're probably going to care a lot about how much memory you use. And so you should never write in Python what you can write in a finite state machine, right? And if you think back to how I wrote the deterministic finite automata, that was a Python dictionary, which is equivalent to JSON. I was just writing JSON. I was not using a programming language. I can express computation in a JSON file. We do not think of JSON files as a programming language. Do we need non-determinism? Yes. Non-deterministic PDA and deterministic PDAs are not equivalent. The example is the reverse. We cannot do that without non-determinism. I'm not going to make you write the proof. Well, maybe I will. We'll see what happens. Right? And now that is time for our stretch break. I was going to say we break for lunch now, and let's meet back here in about an hour.
Yeah.
Cool. And I'll just eat here. I'm going to be around, but you can do whatever works for you.
Well, I think the...
Gonna head over there?
No, I think it should close, because I went to Starbucks.
Okay.
Over there in the library, it was closed.
I think the Lagrange dining hall,
Dining hall, I don't know.
I bet this doesn't open till noon. No, it should be open at 10:30. You can go over there and check it out if you want. And if it's closed, I'm sorry. Come eat some Indian food.
No, it's already.
Okay, cool.